Last class we have seen the equivalent circuit of induction motor. Now we will see the various tests on induction motor. Usually you can conduct two types of tests on induction motor. One is load test or brake test. Another one is no load test and block to rotor test. So load test, otherwise it is called as brake test. That is a very common test applied for any type of machine. That is nothing but simply you will load the induction motor and we will find the performance of induction motor, right? So for various load conditions, how the induction motor is behaving. So that is the load test. Other name for load test is brake test. Performance of induction motor means we will be finding the efficiency. For various load conditions, what is the efficiency of induction motor? So that is the load test or brake test. Right. The second test is no load test or block to rotor test. So this no load test and block to rotor test, it is very much similar to open circuit test and short circuit test in the transformer. So this is equivalent to open circuit test in transformer. In transformer. This is very much similar to short circuit test in transformer. Okay. So load test, I told you that for various load conditions, we will find the efficiency of the motor. So that is the load test. Other name for load test is brake test. The second test is no load test and block rotor test. No load test is very much open circuit test in transformer. Block to rotor test is very much similar to short circuit test in transformer. Okay. So so this is very similar to the transformer open circuit test and short circuit test. So by conducting open circuit test and short circuit test in the transformer, what are the parameters we will obtain? We will find the parameters of the machine. Same way, using this no load test and block to rotor test, we can find the parameters of the induction motor. Parameters means stator resistance, stator reactance, rotor resistance, rotor reactance, core resistance, and magnetizing reactance. So first we can find the parameters of the induction motor. And second, after finding the parameters, we can draw the equivalent circuit of induction motor. And from the equivalent circuit, we can find the efficiency of the machine, output power of the machine, torque of the machine. Okay. So this is the objectives of no load test and block to rotor test. This is very similar to the transformer open circuit and short circuit test. Till now, any doubt is there? Yes. So now we have to see how to conduct this no load test and block to rotor test. One by one we will see. So this is the no load test. The word itself, it is self-understandable. Without adding any load to the motor, there is no load connected to the motor. Very similar to the transformer open circuit. Simply you will be apply the rated voltage and you note down the voltage, current and power of the induction machine. Okay. So voltage you can measure using voltmeter, that is V0. So here this is V0, and current you can measure using ammeter I0, and power you can measure using 2 wattmeter method. Okay, 3-phase power you can measure using 2 wattmeter. 2 wattmeter can be used to measure 3-phase power. Okay. So no load test, you have to conduct the test at the rated voltage. So you have to note down in the table, and current you have to note down, that is a no load current. And the total power, 3-phase power, no, you can get by adding the power which is indicated in W1 and power indicated in the wattmeter W2. So you have to note down the reading. So from these readings, you can find the core resistance and magnetizing reactance. So using no load test, very similar to transformer. Using no load test, you can find core resistance and magnetizing reactance. Okay. So these are all called as no load parameters of the induction machine. In the transformer, it is called as open circuit parameters. Both are one at the same. So how to find this core resistance and magnetizing reactance? So this is the formula. So you know W0, the power equation in 3-phase is nothing but √3 V0 I0 cos phi 0. So from this you can get the power factor. Cos phi 0 is equal to W0 divided by √3 V0 I0. Okay. And this is the equivalent circuit under no load condition. Okay. This is the equivalent circuit under no load condition. It means that you have only the shunt parameter. You don't have any effect of series parameter because there is no load connected to the induction motor. This is very similar to the transformer. Now what is my IC? That is the current flowing in the core resistance, I0 cos phi 0. What is IM? IM is I0 sin phi 0. Very similar to the transformer. So this is the active component or working component or core loss component. Core loss component. This is the magnetizing component. So how I can calculate the core resistance? Voltage by current flowing in the core resistance. Since this is 3-phase machine, you have to take all the values per phase. So V0 per phase divided by IC per phase. Similarly, Xm is nothing but V0 per phase divided by Im per phase. So this is the core resistance. This is the core resistance. This is the magnetizing reactance. Any doubt you have? So the analysis is very similar to the transformer. So it is very easy to understand. Whatever we have done in transformer, the same analysis we are doing here. Right? So similarly, the series parameter, it means the stator resistance, reactance, and rotor resistance and reactance, no, we can find from the block to rotor test. The block to rotor test is very much similar to the short circuit test. This is very much similar to the short circuit test. Short circuit test. So how to do this test is nothing but you have to tighten the rotor of the induction motor using a belt. Okay, you have to tighten the rotor of the induction motor using a belt. Belt means you can use the mechanical load belt. When you come to the lab, I will show the mechanical load belt, and using that belt you can tighten the rotor, and you have to give the voltage to the motor, and you have to circulate the rated current in the machine. So under that condition, the machine will not rotate. It is under short circuit condition, or in other words, it is under blocked rotor condition. Simply you have to tighten the rotor so that it is not rotating when you give the input voltage to the machine, and you have to circulate the rated current. So you have to note down all the readings. You have to note down the voltage, and you have to note down the current, you have to note down the power. So voltage is called as short circuit voltage, that is VSC, and current is called as short circuit current, that is ISC, and power it is called as short circuit power, that is WSC. And from this you can get the values of series parameter. Series parameter means theta resistance, theta reactance, then core resistance and core reactance. And what is the equivalent circuit I will get for blocked rotor test? The shunt parameter is not having effect here. Only the series parameter R1E and X1E will be having the significance. So that is what the circuit diagram is shown. You please take the approximate equivalent circuit referring to the stator side. So R1E, that is the equivalent resistance referring to the stator side. X1E, that is the equivalent reactance referring to the stator side. So now we need to find R1E and X1E. So the procedure is, so from the power formula, WSC is equal to root 3 VSC ISC cos phi SC. So from the cos phi SC, you can get the WSC divided by root 3 VSC ISC. So this is the short circuit power factor. This is the short circuit power factor. Okay. And what is the copper loss? Copper loss is nothing but that is the short circuit power. I told you that it is the shorted condition. So core loss will be very much small. It is negligible. Only you have the copper loss. In the no load test, core loss will be dominating than the copper loss. Okay. So WSC is nothing but 3 times I squared R1G. So this is the copper loss 3 phase. Okay. So WSC is 3 I squared R1G, and cos phi SC is WSC by root 3 VSC ISC. So from this you can get the value of R1E. So R1E is nothing but WSC by 3 ISC the whole square. So this is the formula for R1E. R1E is nothing but WSC by 3 ISC the whole square. And what is Z1E? That is the total impedance of the circuit. Z1E is nothing but short circuit voltage by short circuit current. Okay, short circuit voltage by short circuit current. And already we know the value for R1E, that is WSC by 3 ISC the whole square. So X1E you can get by taking root of Z1E the whole square minus R1E the whole square. So X1E is nothing but root of impedance squared minus the resistance square. So this is the equivalent reactance referred to the stator. So this is the equivalent resistance referred to the stator, and this is the equivalent impedance referred to the stator, and this is the equivalent reactance referred to the stator. And now what is my R1E? R1E is nothing but R1, that is the stator resistance, and R2 dash, that is the rotor resistance referred to the stator. Okay. and X1E is nothing but X1, that is the stator reactance, plus X2 dash, that is the rotor reactance referred to the stator. Okay. So that is what here also I have written. R1E is nothing but R1 plus R2 dash. X1E is nothing but X1 plus X2 dash. So here R1 is the stator resistance that can be computed using multimeter. Okay, simply by using the multimeter, you can measure the stator resistance. So once knowing the value of stator resistance, if you subtract stator resistance from the equivalent resistance R1E, you can get the rotor resistance referred to the stator. You can get R2 dash. Okay, and R2 dash is nothing but R2 by K squared. Generally, K will be taken as 1. The turns ratio in the induction motor, no, generally it will be 1. If turns ratio, if it is 1, then R2 becomes equal to R2 dash. So from this analysis, you can get the value of R1 separately and R2 separately. Separately, you can find the values of stator resistance and rotor resistance. Right? Equivalent resistance first we are finding, then we are separating the equivalent resistance into two. Stator resistance we are finding separately and rotor resistance we are finding separately. And similarly here, X1E is nothing but X1 plus X2 dash. And if you assume stator reactance is equal to rotor reactance, generally it is valid for any induction motor. So if you take any induction motor, if you measure the value of stator reactance and rotor reactance, both will be same. So, and if you assume K is equal to 1, then X1 becomes equal to X2, that is equal to X1E by 2. So, independently, you can find the value of stator resistance R1, rotor resistance R2, stator reactance X1, rotor reactance X2, core resistance and magnetizing reactance. Independently also, you can get the parameters of the induction motor. Till now, any doubt is there? So these are all the approximation we are doing it. It is a valid approximation. We are taking X1 is equal to X2. In that sense, then X1E divided by 2 will be X1 is equal to X2 dash. If you assume K is equal to 1, then X2 dash becomes X2. So here, the short circuit current we will obtain under reduced voltage condition, right? Because already the rotor side is shorted, and since it is a short circuit condition, a very lesser amount of voltage is sufficient to circulate the rated current. That is the short circuit condition. The current will be very high. In order to circulate that very high current, the voltage which is going as the input to the machine, it will be very, very less. A very lesser amount of voltage is sufficient to circulate the rated current. Right? So that is what we found in block rotor test. Now, we can also find short circuit current at normal voltage. Sometimes, no, this is useful in solving problems. This is the short circuit current under normal voltage, right? This one you cannot find experimentally. Short circuit current under reduced voltage only we can get experimentally, because already the circuit is shorted. So lesser voltage itself is sufficient to circulate the rated current or short circuit current. That we can find experimentally, but the short circuit current under normal voltage, that is not possible to find experimentally, because if we are giving rated voltage to the machine under short circuit condition, the current flowing in the machine will be very large. So practically it is difficult to compute, but we can predict that value. So how to predict that? Using ratio and proportion. So what is the short circuit current at normal voltage? That is nothing but the rated voltage divided by short circuit voltage multiplied by short circuit current. Right? Just a ratio and proportion. For ISC, this is my VSC. Okay? For my ISC, this is my VSC. This is the short circuit current. For this short circuit current, this is the voltage I am getting. For the rated voltage, what is my current? Just a ratio and proportion. VL by VSC divided by ISC. So ISN is nothing but that is the short circuit current at normal voltage. ISC is nothing but that is the short circuit current at reduced voltage. Okay. Similarly, you can find the short circuit power also. Short circuit power is nothing but ISN by ISC the whole squared into WSC. This is the short circuit power. Short circuit power is nothing but it is the copper loss only. Okay. Under normal short circuit condition, copper loss is WSC. Okay. But for current at normal voltage condition, copper loss is nothing but ISN divided by ISC the whole square multiplied by WSC. Since the copper loss is nothing but I squared R, so you are getting square of the current here. Okay. Sometimes these two formulas is useful to solve problem in gate examination. So any doubt you have? Any doubt you can ask me. Short circuit power is nothing but it is the copper loss I squared R. So this is the ratio. This is ISC. This is ISC. So for WSN, this is ISN the whole squared R. Just if you divide, you will get it. WSN is nothing but ISN squared divided by ISC squared into WSC. You have to divide these two. That's it. You divide, you will get this. So today we have seen the test on induction motor, load test, then no load and block rotor test we have seen, and from the no load test we can find core resistance and magnetizing reactance, and from the block rotor test we can find the stator resistance, rotor resistance, then stator reactance and rotor reactance, and some two formulas I have given that is useful to solve problems in gate examination. So with this I complete the today's class. Next class we have to solve one problem in no load test and block rotor test. With that your unit 1 will be completed. So till now, are you having any doubt? If you have any doubt, you can ask me. I'll give some time. Anything, anybody you do not understand, any concept or any relationship you do not know how to get that? It is a simple circuit theory only. and the analysis is very much similar to the transformer. Shall we wind up the class today? You have math classes 220. Okay, fine. So next class we'll meet. Thank you all.